if I want to go more in depth about the dispersion forces, I'm going to say that dispersion forces are subject to size and molar mass of the compound. Okay, size and molar mass of the compound. Okay, let's list them. Okay, so the size of molecule and size of the molecule and also shape of the molecule will affect the dispersion. Okay, so here are some examples. Okay, so we have CH3, CH2, CH3 versus CH3, CH2, CH2, and then CH3. Okay, I'm going to say dispersion force subject to size or molar mass. Okay, and so here, example that I mentioned. Okay, I have one that is the molar mass for it is going to be 36 plus 8. That's going to be 44. So the molar mass, okay, for C3H8 around 44. Okay, molar mass for C4H10. Okay, so we have 40. Okay, we have 12 multiply 4. That's going to be 48. 48 plus 10, 58. Around 58 gram per mole. Okay, so I'm going to say boiling temperature. Okay, so boiling temperature for C4H10 will be higher than boiling temperature of C3H8. Okay, why? Because it has higher dispersion force. Okay, it has higher dispersion force. So I'm going to say the dispersion force for butane is higher than propane. Okay, and that's one. So as the molar mass goes up, dispersion force it will go up, and the boiling temperature it will follow it. Okay, another one. So dispersion force subject to size. Okay, size of the particle, or we can say molar mass. Okay, remember, size, okay, to the right side of the periodic table increases, down in any group, forgive me. Okay, yes, size to the right side of the periodic table, size to the right of the periodic table decreases, down in any group, and increases. Okay, down in any group, it increases. Okay, so for example, we have fluorine, then we have chlorine, and that's going to be, let's say, bromine. So I go fluorine, bromine, chlorine, and bromine. Okay, as you go down, the molar mass is getting bigger. The size also will get bigger. Now, if I take two fluorine and attach them to each other, okay, yes, we will have intermolecular force. We will have, a chemical bond between them, but also we're going to get hydrogen bond. We're going to get dispersion force. Okay, if I just simply copy paste these two and put them close to another one, okay, another one. So I'm going to say, if you look to these two, area that's available for interaction between them, it will be really, really tiny one. Okay, and if I bring, like let's say, if I bring this one really close to it, okay, and zoom on it, this is going to be the one that they are in touch. Like in that area, they are in touch. If you compare it with chlorine, that one got bigger. Okay, next, if you move to bromine, again, it will be bigger. Okay, so as we increase the size, the area or the surface that's available for interaction between two molecules, it goes up. So in that case, we say the dispersion force got stronger. Okay, the dispersion force got stronger. Dispersion force not only subject to the size or molar mass, okay, also is subject to the shape of the molecule. If it's linear, it's better. Okay, linear is better versus like completely spherical. Okay, okay, so linear is better than spherical. And this is one example. Let's say we have this molecule. Okay, so I have we have here one there one. I think we can go with maybe 4 of them. Okay, this one is linear, and you can take this molecule and rearrange it this way. Okay, so I'm going to erase one of the hydrogen. So let's say this hydrogen is gone. Next, this piece I will chop it. and I will attach it here. Okay, the hydrogen that I cut, I'm gonna put it there. Okay, so now what happened? We got one branch. This is the main chain, and we got one branch here. Okay, remember the main branch used to be that one. Okay, so we're gonna repeat this. Okay, I can do it a couple of times. Okay, I can, like, let's say, put another one, for example, this way. So we had one here. Okay, we can cut this and transfer it there. Okay, so let's cut this one, and we're gonna put it here. Okay, and this time each carbon is gonna have 3 hydrogens. Okay, now what happened? From linear geometry, we started to, shifting to kind of a spherical geometry. The last one, if I draw something around it, I can say it's almost like a spherical object. Okay, well, the first one was completely linear. So the first one was completely linear. The second one got a branch, the third one, and the third one now turned to be spherical. Remember, I did not change the formula for all of them. So the formula for all, okay, for all of them, I have this formula. I'm going to write it there. I have C5 for all, and H is going to be 5 multiplied 2 plus 2, it will be 12. Okay, so the formula did not change. Because the formula did not change, the molar mass did not change. So should I get the same, dispersion forces? The answer is no. Which one has the strongest dispersion force? Let's talk about it. Okay, if you have a linear geometry, you can get something like this. Okay, called zigzag geometry. We have 1, 2, 3, 4, 5. Each of this represent 1 carbon. Okay, each one represents 1 carbon. So this is a carbon that's attached to hydrogens. Okay, and what do we have here? We have 2 hydrogens. Okay, and I can say that hydrogen, technically, they are attached to carbon. Okay, I can put next molecule somewhere here. So I'm going to put the next one somewhere, say here. Okay, entire of this space, it will be available for dispersion force or intermolecular interactions. So I'm going to get some interactions here. Okay, I have more area for interactions. So I'm going to say the dispersion force is up, is really high. Okay, if you start making, if you branch this one, branching is going to mess with the packing. Okay? It's not going to be perfect. Okay, and if you turn it to spherical, you're not going to have much space actually, or much like technically area for intermolecular forces or interactions. So if I put the neighbor one somewhere here and attach them, okay, so if I attach them, I have just that tiny area, okay, available there for intermolecular forces. Okay, so if you compare these two, clearly the linear geometry has higher dispersion force. So which one is going to have the highest dispersion force? I'm going to say number 1. Okay, so the the trend for dispersion force will be number 1, then number 2, and number 3 is the least. Okay, so if you want to talk about boiling temperature, I'm going to say boiling temperature for number 1, it will be higher than number 2, and number 3 is the least. Okay, number 3 actually is gas. If I remember correctly, I believe it's gas. Okay, if it's not gas, it's going to have really, really low boiling temperature. That means you can easily boil it. Intermolecular forces, we use them. Okay, we use them to technically get a homogeneous mixture, or we use it for the purpose of solubility. Okay, so let me go. Okay, here, let me go through the slide. So what's the miscibility? If you want to have a homogeneous mixture, okay, you need to check polarity or non-polarity of technically the solvent or the liquid that you're dealing with. If you want to get a homogeneous mixture, you should mix polar with polar, non-polar with non-polar. Otherwise, if you mix a polar with non-polar, you will get a non-miscible mixture. So technically, you will get a heterogeneous mixture. Okay. And whenever we are, trying to clean, like say dirt or anything or grease from our, cloth, we use like soap. And any soap, it has two sides. One is going to be hydrophobic area. The hydrophobic area is non-polar. Okay. And there will be a head, and that head is going to be a polar side. Okay. And why do we do it? Because like most of the greases that we get, like they're coming from like meat or any like food that we eat, it has a big chain, okay, big chain of like non-polar stuff, and the solvent or the liquid that you use is water. Okay, you need to have a soap that is soluble in water. In order to make it soluble in water, we need to have that polar side. Why? Because water is soluble. Okay, water is soluble. Forgive me. Water is a polar solvent. Your soap supposed to be soluble. In order to make the soap soluble, we need to have a polar head. So that's the purpose of the polar head. Next, grease is non-polar. Grease is attached to to the fabric, your cloth. You want to pull the grease out of the fabric and dissolve it technically in water. And in order to pull the grease, we need to have a non-polar chain on the soap. Okay, and that's the purpose of it. Okay, so like as you see here, we have like a grease or whatever, and the soap is reaching it from the non-polar area and trying to technically grab the grease. Now that we have the grease, okay, so if the white one, for example, if the black one is the soap and the white one is the grease, okay, it's going to reach it from this tail, which is non-polar. Okay, they will attach it. Now the head is a polar, and it will go inside water. And that way we can slowly dissociate actually the grease. And when dissociate the grease, now they turn to a smaller particle. And so the dispersion force between them, it will be less. If it's less, their solubility very soon will be, higher in water. Okay. Now, before I end this lecture, I want to talk about the sickle disease. And what's the sickle disease? Okay. So any hemoglobin has 4 core. Okay. So let's say this is our hemoglobin, and it has 4 core. And what do we have there? We have iron, okay, iron that attached to a bunch of nitrogens, okay, and we call them porphyrin. Okay, and that's going to create technically the red cell. Okay, red cell is supposed to carry oxygen, and the way it will carry oxygen, it will be attached to this iron, and it can carry it to the cell. Now, somewhere inside inside this complicated protein, we have, imagine we have something like this. So this is a piece of like, let's say, protein that is bented or peptide bented. And okay, in one area, we have this molecule. So I'm going to write structure of any amino acid. Any amino acid, you have a carbon. And one side, you have carbon attached to 2 oxygen. Okay, this one will be the acidic side. Other side, you will have nitrogen with 3 hydrogen. It will have a positive charge, and here we have a negative charge. And how about carbon? Okay, carbon, it has hydrogen, and there is here R. And what's the R? Okay, R, okay, it can be 1 carbon, 1 hydrogen, or other stuff. Like we have a 20 amino acid, I believe. Yeah. And how do we get the 20? We change this R or the alkyl group. Okay, you can say alkyl group. Okay, and again, the R, it keeps changing. It can be CH3. It can be just simply like an H, or say ethyl, or other groups. Okay, now if you take this, for example, here we have an amino acid. Let's say, okay, we have an amino acid, and that amino acid is this one. Okay, so we have a carbon. Okay, carbon, and then carbon here. Next, we have C attached to O, and then here O. Okay, that one, let's say, okay, let's say here you have COO minus, and then I'm going to say here, that one is, you have NH3. Okay, let me attach this one there. So say this one here is attached there. Okay, Now, this one is ionic, or it has a positive charge. Okay. And so in order to have like any interaction with this piece, we need to have another one is ionic here. If it's ionic, these two, they will get interacted, and they will have interaction, and it will twist. Okay. And the one we have here, the one that we have in front of it, is non-polar. Okay, non-polar. Okay, and because it's non-polar, they will not interact, and the shape of the red cell, it will be almost flat, and it can easily carry oxygen. Okay, it can carry oxygen. Now, if you change this amino acid to this one, okay, so take this yellow group, get rid of that one, and the carbon that I deleted, okay, I'm gonna put it here. I'm gonna attach it to that one. Okay, so if I get rid of this carbon and just simply attach it to this one, now I'm gonna get non-polar group there. Okay, that non-polar group is gonna have interaction with this one. Okay, and because of that interaction, structure of the cell, it will change, and it will turn to this shape. Okay, and because we change, technically, because the structure of the protein or the cell got changed, efficiency in carrying oxygen, it will go down. Okay, and unfortunately, like if the mutation is huge with one person, that person is going to be dealing with some complication. But you need to have like at least like I believe at least in three sites mutation, and then you get like disease. It's not like if one of them happen, and then that person will be sick. But interestingly, people that they are dealing with sickle disease, they are stronger. They have strength when it comes to malaria, and I don't know what's the reason behind it, but is a true fact, and they proved it in Africa that those people, they have more like strength against malaria. Thank you very much, and have a great time.